Good morning. Welcome to the second talk. Probably it's a little bit noisy. It is okay? Okay, so today I like to talk about theories. Real theories, and including gauge theory and also the numerical simulations. And first of all, I'd like to remind you that I have already introduced a model, probably with which we can discuss some experimental aspects of the magnetic real spiral laws, which behave like a quantum spin systems. But before going to the details of the gauge theory aspects, it's quite instructive to imagine what may happen if you have such kind of interactions. And this is the okay. May I have a pointer or? No? Okay. Okay, yeah, I know. And if there's a USB memory, USB stick, which can control the slides, the buttons, that would be great. Maybe somewhere here. Okay, so in any case, seems nothing. Okay, so let us consider this spin flip interactions, and the effect of this is quite simple. So we are starting from a spin-nice vacuum, which has extensive macroscopic degeneracy, but we can fix one of them, and then apply this interaction. So then we immediately get a spin exchange. So one pair of that in-out will be flipped like this. But then we expect that this radiates some excitations, and then we end up with creating monopole, anti-monopole charges, or we call spin-ons. And spin-on and anti-spin-ons, or spin-ons with plus or minus charges appears. Okay. So this will provide the transfer integral or kinetic energy of the spin-ons or monopole charge, so-called spin-as monopole charge. That is the one effect. And another effect, which is more prominent, if we start from the classical spin-nice, is the following. So suppose we have this kind of flippable hexagons in a bracket. So then apply these interactions 3 times successively, and then we immediately flip all the spins. So then if we count the change of the spin-ons or monopole charges, so then actually if we start from here, and then plus and minus monopole charges will go around in the opposite direction. So then it ends up with some flux and associated with some gauge fields. And it's possible to assign some gauge potential on each diamond lattice link, namely on a particle lattice site. So then we can write this gauge flux with as a curl A. Okay? And then depending on the sign of this interaction, since it appears as a third-order perturbation expansion around the spin-nice monopole, then depending on this sign, we can get zero flux or pi flux. Okay? This will be deconfines the monopole charges. So then we can start discussing U1 gauge theory with and without matter fields. So I will give a blackboard talk from now, but here is a basic summary of the gauge mapping. So this is the kind of building block of the Picor lattice, which is composed of two nearest neighbor tetrahedra, and which share the spin here on the Picor lattice side. And the dual lattice is a diamond lattice. So the diamond lattice side actually sits on the center of the tetrahedron. Okay, so then let's assign the SZ on this Picor lattice side with electric field in a gauge theory. And electric field should be a directed variable. So we assign some sign depending on the direction. So whether it goes from upper tetrahedra to downward tetrahedra or in the other way. So if we make this assignment, then we need similar mapping for the S plus or S minus, and which flip spins. So okay, so if we start from this configuration, and then flip spins, so then clearly the multiple charge or spin-ons should be transferred from here to there or the other way. So it means that we change the configuration of the charges. In that sense, we need to apply some creation and annihilation operator on A and B sides of the diamond lattice, which is represented here phi dagger and phi. Okay, and without anything, we cannot satisfy the computation relations of the spins. So we need something else, which is actually written here as a compact gauge field, U1 gauge field. So e to the IA is associated with some gauge field, which is conjugate to electric field. And if we satisfy this commutation relation between A and E, then we get recover commutation relation between the SZ and S plus or S minus. Okay, that's the way how we construct the gauge theory. And then actually this phi dagger, I already mentioned that the phi and phi dagger will be a creation annihilation operator with the gauge charge. And the gauge charge should be constructed as the sum of the force SZ on a single tetrahedron. And so we can define lattice divergence of E and as a gauge charge on A or B diamond lattice side. And so since phi and phi dagger should change the number of Q by plus or minus 1, so we need to introduce this commutation relations. And then the easiest way to construct this is e to phi, associate phi with e to the I phi. And phi should be the wave function of actually spin-ons. And phi should be conjugate to actually this charge Q. So physically the charge Q should be the charge of the spin-ons, and the phi should be the charge phase of the wave function of spin-ons. Okay, and we can introduce this complex scalar field phi under the constraint that phi dagger phi should satisfy this local constraint. Okay, and then since all the fields all the gauge fields are U1, so we can expect U1 gauge theory should be describe this situations. Okay, so now we have a Hamiltonian starting from the Ising part, okay, and plus S plus S minus interactions. And of course, there are some other terms, and, which I will omit for the moment, because I mean, to make focusing on the simplest cases will be, better for understanding. And okay, and let's. Sure.
So the fact that Heidegger phi should be 1 should be imposed as a Lagrange multiplier somewhere in the.
Excuse me.
The fact that Heidegger phi should be 1. The constraint should be imposed in your field theory, right? So there should be another Lagrange multiplier.
Right. Exactly. Yeah, but this is a Hamiltonian. Okay. So Hamiltonian can be defined under some constraint, right? But if we introduce Lagrangian, then we need a Lagrange multiplier. That's the way how we proceed. Okay. So according to this mapping, so we have so I use capital R for denoting the diamond lattice sites. So this is diamond lattice site. Okay. And I just, rewrite this Ising part. Okay. And then you have then we have this this Hamiltonian. And actually, this B, the vector from this, the lattice vector from one diamond lattice side to the other nearest neighbor. So we have 4 different sublattice vector for B. So mu runs from 1 to 4, or 0 to 3. Okay.
So in the top line you wrote on the board, are the couplings for the ZZ and the XX parts the same?
Yeah. Do you want other terms? Exhibit right on?
So I thought that the coupling in the Z part is much greater than the XX.
Oh, okay, sorry. Yeah, you're right. So I introduced some parameters here. Yeah, sorry. This was Heisenberg. Okay, so okay. So then it turns out that this is a kind of Bosonic model. So phi is a bosons. Yeah, the reason why we assign bosons to phi is the following. So if we start from the spinized vacuum, so the defects, the spin-ons have a quite large energy gap. So there's no gapless excitations. And of course, it's easier to assign bosons to such kind of excitations. And that's one reason. And the second reason is that if we assign fermions to the spin-ons, then it's not possible to discuss the Bose condensations, which can be, which should happen in real spin systems, like in ordered phases. So to describe both the ordered phases and deconfined phases, it's better to assign bosons. And actually, energetically, it turned out that assigning bosons to phi is much lower the energy. Okay. But of course, if you have some more different cases than we consider, then I mean, of course, there's some more options. Okay. So here we assign bosons. So then this is a kind of kinetic term for bosons. And so we can expect Bose condensations, right? So if this term dominates, okay? And actually this will happen, and which I will explain later. And going to the Lagrangian is quite easy. So we have H first, and then minus I Q of phi. Or actually, if this phi dot can be represented as phi dagger, I to the phi dagger phi dot, okay, under the constraint. Okay. And then we also need to assign the commutation relation between A and E. So we should have, let's go with this. And we need to implement a constraint. And there are several ways to assign constraint, but the easiest way should be at this term. Okay. And this is one of the constraints. And then there's another constraint of the Gauss law. And we assign a scalar potential and this charge and divergence C, of course, and scalar potential living on diamond lattice side, and this also living diamond lattice side, and this is living on the diamond lattice link. And H contains a quadratic term in Q. And so then we can integrate out degrees of freedom of charges. Okay? So then actually it provides a this is gauge covariant derivatives, second derivative of phi field. And then kinetic term of spinel. And like this. Bigger font, you mean?
Yeah, and
Okay.
little more harder, so that, sorry.
No, sorry, no. Okay. It's probably. Actually, this should be minus. Okay. 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 So then, actually, we have a U1 gauge theory with the matter fields. E and A are actually the gauge field or the electric field, as in the case of the lattice QED. And phi describes matter fields. Okay. And now everything is gauge covariant. But of course, I mean, we cannot discuss anything with this, I mean, without making approximations. It's quite hard.
That last term doesn't come like Q minus Q.
This one. So we implemented the Gauss law constraint, right? So Q is actually originally there's no degree freedom of Q, and Q is nothing but just the sum of the divergence, sum of the electric field, and this is just a rephrase of E R plus B mu.
And now we've integrated out Q, right? So
Sorry, yeah, you're right. Okay, so this term is gone. Now this term is gone. Yeah, you're right. Thank you. You're right. Huh? This one?
No, the one above.
Oh, you're right. Yeah. Okay. Eta, yes. You're right. Okay, so then we make some saddle point approximation. And the point we made, actually I forgot one more constraint. Actually, the electric field should satisfy this constraint, right? So now we are treating the Ising degrees of freedom or spin 1/2 degrees of freedom, so that we need to we make this constraint fully satisfied locally. So we can add one more. Okay. Well, we have another Lagrange multiplier. Okay. Okay, so now we make an approximation. The first approximation we should make is about the scalar potential. Okay.
So, this EV plus half or minus half, of course, that's a microscopic constraint, right? But does it matter for long distance properties if I keep a 1/4 there or not?
This term?
Yes. I mean, suppose I just say E squared. Does it matter for long distance problems?
Not too much. But actually, this critically determines the velocity of the photons. Yeah, yeah.
So this 1/4 is because you're considering split half.
Okay, so for 1/4, this part, yeah. So actually, this is kind of a frustrated lattice gauge theory, in a sense that it cannot be 0, right, locally or from time to time. Always takes 1/2 or -1/2. And if it is allowed to have a 0 value, so then actually nothing happens. I mean, over the crystal, there's no electric charge, so no gauge field, so nothing happens. It's a boring state. But the reason why we can get an interesting state like a deconfined Coulomb phase is that E can take either plus or -1 or -1/2. Yeah, so in that sense, it's important, right? So if we drop this term completely, so then E is 0. So this gives a boring theory. Okay. But of course, we can change this number to some another constant, and that will not change the long wavelength physics. And now we make a saddle point approximation. Okay, maybe take this average, and this should be 0. 0 everywhere, or some constant. The reason is the following. So if we introduce some potential, so then we make a profile of the gauge charge. So Q can be distributed over the crystal, and this will completely cost energy of the this Ising interaction. So we can make this 0. Okay. And then we can expand this phi field around saddle point, which is 0. So then integrate out delta phi. Okay. And we have actually five fields from this term, but the linear term should vanish. So we have just quadratic terms, and this could be integrated out. So then this combining quadratic term in phi and this, then we recover the original term of this. But actually, this commutes with the other term in the Lagrangian. So actually this is gone, completely gone. We can forget about this. And the rest of the Lagrangian is written like this. Oops. But this already non-trivial Lagrangian. This is non-trivial Lagrangian because E and A are coupled to matter fields. And then we need further approximation. So the approximation we made is the following. So let's separately consider the charge 0 sector. That means the Q equals 0. And the charge 1 sector. So charge 0 sector should be treated only with gauge fields, E and A. And Q equals 1 sector should be provided by solely by the phi fields. Okay, this is the approximation. But we take into account the each other effects, mutual effects as a kind of mean fields, or assume they are all frozen. Okay, that's our assumption. So then we can replace with this another color. Like a average. And okay, so this term should be accompanied by this potential term or mass term. Okay, and then okay, so this is matter field part. L1 and L0 for charge 0 sector. It's given by this, and then actually some non-trivial thing happens. So there's no way to construct a gauge invariant or gauge covariant action or Lagrangian from this term. Because these gauge fields are always associated with creation and annihilation of spinons. Only when we create annihilation of spinons that gauge field may appear. Okay? So, so the one way or most plausible way to construct non-trivial effects from this term is actually add the term which I already explained. Oops. Yeah, so the lowest order effects of the gauge field must be accounted by this effect. So then we when we try to construct a gauge invariant or gauge covariant action for the charge 0 sector, which actually we completely dropped out in a paper with the neon balance, it's combining this effect. There's some numerical factor which may depend on the representation. And then we have cosine Kale. This is the only way, in the lowest order, to include the non-trivial effects of the gauge fields. Okay. now we get these two different kinds of actions. Now, of course, we need to add some, counter terms, and because we have made a kind of mean field decoupling, so we need to, subtract some part, but that is constant. So for the moment, I will forget. And okay, so let me start with this part. Let's start from the ground state, which is easier. So then when we make an approximation for these parts, it's quite easier to consider that each part is completely independent, right? Independent variable. So this part and this part, we treat them separately and as a mean fields. Now this is actually based on a very old idea by Wilson of the mean field. For the lattice gauge theory. I forgot the year when the paper was published, but probably 50 around 60. Okay, and then it turns out that actually we need a projective symmetry group analysis, which partly explained yesterday by the Shubro, yeah. And actually, in that case, actually, the equivalent gauge group was just D2, so plus or minus 1. Gauge field can take a plus or minus 1, but now we can take a continuous number, right, as for the phase. So we have e to the I phi, like e to the IA. And A can take any number from 0 to 2 pi. Okay. And then performing a gauge field performing a projective symmetry group analysis, and actually we need to construct a similar, algebraic equations that Shubro discussed. Yeah, for instance, we need to consider how this behaves. And since we have more complicated lattice structures, which is given by the FD 3 bar M. So we have mirror symmetries, and the 3-4-4 rotation symmetries, and 2-4-4 rotation symmetry, and so on. And of course, time reversal. And we need to actually treat all of them, and which is quite lengthy and takes probably 20 to 30 pages to note. So it's not possible to do that here. But if we do that, actually we've found several possible states to describe this ground state. And the ansatz we made is that when delta is negative, we can take all the A can be 0. I mean, A can be actually uniform. So it means that in the gauge space, or in a space for the spinons, there is no translation symmetry breaking. But for delta positive, actually A can take 0 and pi, depending on the size, and which enlarge the unit cell in the gauge space. But this doesn't break physical symmetry at the end. Okay, so when delta is negative, so then we have uniform gauge fields, and this term drops out. So we just have some free boson, except that it should satisfy the constraint of the phi square should be equal to 1. So then we can expect both condensations, right? But on the other hand, when delta is positive, actually this is already frustrated. So it turns out that it has when we diagonalize this Hamiltonian, Lagrangian, so then the dispersion for the spinons, we can compute dispersion of spinons. So then actually there's a several branch, and the lowest energy branch, it has a line degeneracy. Maybe too small. So which means that the spatial dimension of spinons is reduced by 1. Okay? So then it's quite hard to achieve the Bose condensation, right? So then it turned out that when delta is positive, actually Coulomb phase persists actually at least until Heisenberg point is reached. So this means that spinons remain gapped when delta becomes 1. And when delta becomes 1, we have a Heisenberg or SU2 symmetry. So we can no longer rely on this theory. So we need to more elaborate one. But at least as far as these terms are concerned, U1's quantum spin liquid is stable. And this is nothing but U1 quantum spin liquid. The spinons are gapped. And for delta negative, we have actually some instability at the finite delta. And it turns out that when delta is, I've got a point number actually, around 0.2, I guess. Yeah, something like this, 0.2 minus, sorry. So then eventually phi becomes finite. So we have both condensations, right?
So both these statements, they are the mean field theory results, right?
Mm-hmm.
So it's entirely possible that the Coulomb phase sort of goes to something else before the Heisenberg point.
Yeah, of course it's possible beyond mean field. I mean, but this is the starting point.
Right.
Yeah, but actually, when delta is positive, I would go back to this point when I show numerical simulations. But unfortunately, this case cannot be treated by quantum Monte Carlo because we have a negative sign problem. So the issue is actually remaining open. So whether it may, Coulomb phase is stable until the Heisenberg or not. So there should be something, I mean, at least at the Heisenberg point, or maybe before. But it's completely open. Okay, so I say that it's a Coulomb phase, but actually I didn't, prove that. So to see that, actually we need to treat this charge 0 part. Okay. So probably I can erase this first line.
So we have line degents in the excitation.
Mm-hmm.
Are they bosonic excitations?
Bosonic, yes. We assign bosons, right? Assign phi as bosons. So, I mean, the spatial dimension is, a bit lower, right? And at the final temperature, at least, it's a 2D, so it's not possible to get the Bose condensation. And only at the Z temperature, it might be possible, but it's quite hard. Yeah, probably the answer would be yes. Of course, there should be certain symmetry, which guarantees the line degeneracy. But probably that is one of the symmetry included in this space group. But of course, if we go beyond, like if we include the further neighbor hoppings and so on, it might be possible. But there's some arguments. Okay, so I can tell you now. Okay, of course we can include further neighbor interactions, S plus, S minus, for instance, 1, 3. Here is some Kagome lattice, part of the Kagome lattice, and here is my spin, side 1, side 2, side 3. Yeah, for instance, we can include this kind of interactions. Probably we need the other way. We can exchange these spins as second level interactions. But when we do that, charge will be hopped from here to there, right? And charge hop from here to there. So which means that we have phi dagger, phi dagger. Okay, so it is actually chaotic interaction terms, and this, in 3 plus 1D, actually this is irrelevant. So the small coupling constant cannot change the ground state. Okay. Of course, if we have a much larger interactions, it's quite hard to guarantee that guarantee the Coulomb phase physics may persist. But in reality, the further neighbor interaction should be smaller, so that should be okay. That's the argument. Okay, so now we any more questions? Okay. Yeah.
That is in 2-dimensional case, but here we have 3-dimensional case. So how to define those?
Okay, so so this is kind of I cheated somehow. So in reality, yeah, for instance, we need to do actually, the hexagon should be the closest, smallest closed loop. So we need T1, T2, T3, T1 inverse, T2 inverse, T3 inverse. So we need to make up this product. Okay? And for the mirror symmetries, actually it's quite complicated. And so this is actually translation, and there's some mirror symmetries and C3 rotational symmetries, on-time reversal. And yeah, there's some combinations. And we need to trip all of them, all the combinations, and to classify the possible non-trivial states. And some of them are equivalent, but some of them, of course, not. And then we try to find that which will be the ground state of the model. I mean, at least in the simplest model. And when delta is positive or negative, and when we do not have other terms, it's quite easy to discuss energetics. And so then we could, get this. But I mean, this explanation of this will take, maybe 2 days, 3 days. It's not possible to do that here. Sorry. Okay. So this is okay. So are there any more questions? Or so then okay. So if not, I can switch to charge zero sector.
Just one quick question. So you can list this. So did you say that the line degeneracy of the spin-on dispersion is it only present for delta greater than 0, or is it present for greater delta?
Oh, okay. So line degeneracy appears only in this case.
Oh, I see.
Yeah. So when delta is negative, no, there is no line degeneracy. Yeah.
Okay, so then it's plausible why the thing persists till the Heisenberg.
Yeah. Okay. Okay, so let's consider this action. It's quite simple. And we know that compact case theory cannot be easily non-compactified. So non-compactified means that we expand this e to the IA with some power in power sheets. But actually, in some limited cases, it was justified to describe the long wavelength physics. And that is the case for the Coulomb phase. So actually this, since people here are experts in, I guess, QED or Maxwellian dynamics, so you immediately know that this is nothing but magnetic field, right? So then, actually, the cosine B can be expanded sometimes, right? So when B is fixed, B could be 0 when delta is negative. And B could be pi when delta is positive. But in any case, we can expand, right? And then, okay, so when this is expanded, so this gives a plus, and some coefficient times absolute value of delta. Right? I mean, we need to expand around the minimum. So then 1 minus 1/2 of Cauchy squared. Okay, so this Cauchy is actually the sum of the all 6 gauge potential around hexagon. And we can insert them and then make a Fourier transformation. Right? It's quite easy. And the other terms are completely local. This term is local, this term is local. But here is another problem, which I didn't mention earlier. That is actually the gauge fixing problem. We need to fix gauge. This happens all the gauge field theory. Okay? And actually, there are several ways to fix gauge. And in general, actually, because this is a quantum theory, actually we need to add so-called RXZ gauge fixing, which is it's written in this term. Yeah, in general, we need to add this term. It's just very complicated. And but in the particular case of xi equal to 1 gives a Landau gauge or Coulomb gauge, radiation gauge. And when we add some board condensed spot here, and then it could be a unitary gauge. So the convenient phase choice, it actually depends on the phase we discuss. But here we want to describe the Coulomb phase. So we take a Coulomb gauge. That's most convenient. And in the Coulomb gauge, we can add, of course, because we have already integrated out scalar potential, we can just add divergence A, terms. That is divergence. Okay? To this gauge field, pure gauge field action. And actually, to do this math more rigorously, in a sense of the quantum theory, so actually we need to do a more complicated thing, like introducing a Faraday-Popov ghost. And yeah, but that's kind of technical issue, and actually doesn't change low energy spectrum at all, at least in the tree level. That's a mean field approximation. So now we forget about the Faraday-Popov ghost and restrict ourselves to the semi-classical theory. Okay? We are making a semi-classical approximation. So actually, it's quite easy to see that this term commutes with the other terms, like Carlier. It's quite easy. This is actually, this survives only when the A is longitudinal. But this term survives only A is transverse. So quite easy to see that they can be decoupled, which means that we need to look for the transverse component of the A fields. Right? So then it turns out that AK should satisfy. AK now, there's a AK mu. This is a kind of fully transform, inverse free transform of the original A field. So then there should be at least 4 modes when, okay, so yeah, there's 4 modes independent of the sign of delta, because it doesn't enter the theory. It just changed the saddle point of A, but when we expand A, so in that sense we are treating the fluctuating part of A field. So as far as we consider the fluctuating part, there's no symmetry breaking in the gauge field space. So then we can have 4 modes. But as I mentioned, we need to fix gauge, and we need to take a transverse component. So then the two of them actually drop out. So it remains, there remains only two modes. That is a spin 1 particle. That is nothing but photon. And the two modes are completely degenerate. Actually, this provides another way to derive the gapless linearly dispositive photon modes. And one way has already been provided by Owen Benton and Nick Shannon. That is a kind of, they take actually Hamiltonian formalism and keep the second condensation formulations. But as I mentioned, to keep everything rigorous, actually we need to introduce a variable of cost. Yeah, otherwise it's not correct treatment, in a rigorous sense. Yeah, so in that sense, this will be it's not quantum theory, but semi-classical theory, but still, still works. Okay. So I think I already explained most of the part for the U1 gauge theory with matter and without the matters. So if we forget about the matter fields, then we can just concentrate on this part. Okay. And of course, we can make a feedback of this gauge field part, try to include some fluctuating part of the gauge field into the, when we consider the spin-on problems. But that has not been made, and that's a work in progress. And but quantitatively, it doesn't change the any aspects. Okay, now let's try to include other interactions. Okay, so before going to that part, I can discuss what may happen at the finite temperature. So if we, okay, so everything we explained, I explained so far was restricted to the ground state. The ground state, the reason is that e to the IA can be taken as a plus or minus 1. So we completely freeze the gauge. Right? But at finite temperature, of course, it may fluctuate thermally. So actually, we treated this as a mean field, and we took them as equal to plus minus 1. But it could be, less than 1 at finite temperature. And of course, at a very high temperature, this guy should be gone, right? And there should be some phase transition, at least within the mean field. That was discussed by Savary and Valence, 2013 in peer review paper. But this is actually spurious first order phase transition. And actually the Wilson, when Wilson gave the argument on mean field theory for the gauge field, actually he already noted that there should be several spurious phase transition or sometimes phases may appear within the theory. And okay, so if we naively perform this mean field treatment we call gauge mean field. There's a first order phase transition. But I will show that this does not happen in the real spin model from the numerics. Okay. But yeah, okay. This is spurious. So now we can add so-called J plus minus term. Or yesterday I said that J Q term. Actually, there's difference in the phase convention. Yeah, so factor 2 different. And there should be a phase factor here. And actually, I didn't explain yesterday, but this phase factor appearing in this interaction actually depends on the bond direction. So this can take either 0, phi can take either 0, 2 pi over 3 or 4 pi over 3. So depending on the direction, okay, there are 3 different directions in the model. Okay, but this is not quite important. Okay, so then, okay, if we consider this term and apply the same mapping, okay, and here actually introduced now we need this configuration because we flip 2 spins in the same way. So this is side 1, side 2, maybe this could be side 3. And then we assign this diagonally side at side 2, and here side 0, side 4. So when we flip these 2 spins from both in to both out, so then we are transferring charge from here to there and here to there. Which means that this again gives an interaction term. Like this. And so, I mean, as already I mentioned that interaction terms in this 3+1D model is irrelevant in a normalization group sense. So it doesn't change whenever Q is small. But when Q becomes large, actually it may happen that phase transition occurs to another phase. And it's particularly interesting to look for a possibility that we have a double charge. This is actually the I'm just talking about the one possibility. I mean, could be interesting. And this could be, when this happens, actually this is a charge to Higgs, like in the superconductors of bosons. So
But if you have a charge to Higgs, you can even have some Z2.
exactly, yeah. That's why I'm saying that it could be interesting, yeah. So charge to Higgs phase is nothing but Z2. G2 gauge field theory. So it's possible that the non-trivial topological G2 topological phase may happen. So we try to find that phase, but eventually, unfortunately, we didn't have that phase within this model. And in reality, what we have is always a Bose condensation of single charge. Yeah, so that's charge one Higgs phase. So this is, I mean, adiabatically connected to, I mean, conventional magnetically ordered states. But actually, the pattern we have for this Bose condensation is a little bit different from we had without this Q term, but delta negative. So this is another phase. Yeah, I will go back to this pattern, ordering pattern in this slide. Okay. So this is a one extra term, and another extra term is so-called JZ plus minus, or actually they had a minus sign here. So I mean, minus sign may appear in the Hamiltonian or sometimes not. So it's a little bit complicated, but I took, yeah. So JZ and J plus or minus. With okay, so I should multiply factor of 2 here. So then it's easier. Okay. So there's another term like this, as Hamiltonian conjugate. So this term appears when we consider the Kramers ions like ytterbium, right? And this term becomes, this is the electric field. Actually 0 to 1, or 0 to 2, sorry. And 2 to 4. In this notation. So again, this takes the form of the spin-on hopping terms if we take E as a constant. But without any long-range order of the electric field, this should be fluctuating, or in a static sense, it should be 0. So in the mean field theory, this term does not arise. So I mean, this term is completely gone. But when E is finite, as in the case of the ferromagnet, then this term gives sublattice hopping, intersublattice. And this time, this kind of intersublattice hopping was not there when we considered only delta model, because it just gives a second order hopping on the diamond lattice side. But this term connects A and B diamond sublattices. I mean, FCC sublattices of the diamond lattice. Okay. So then it turns out that I mean, this has already been given by Savary and Barrett. In 2012. This gives another Coulomb phase. But with a ferromagnet. So E is long-range ordered. Actually, E forms a twin-to-earth structure. But because of this sublattice coupling, and it means that if we take this mean field decoupling, if we decouple E and this part, I mean, without, by fixing A feed, then we have a term like mean field variational parameter like phi 2 dagger and phi 4. And this should also be non-zero, okay, when E is finite. So actually, this is nothing but the transverse component of the spin. As you may notice from this definition, okay. So this also gives S plus or S minus non-zero. Okay. So there should be some tilting of the spins from the 111 directions. So it should be tilted. Maybe better use another color. It's the same. Depending on the sign of this interaction, it could change the spin alignment to a more collinear way or the other way around. Okay. Okay. So I think I already finished most of the part, and it's how many minutes do I have? Am I finished?
8 minutes, sir.
Okay. So then I think I should accept questions.
So there's some time for questions. So do the analog of this on this checkerboard map, is this on this 2D, 3D problem?
For 2D, okay, so if we go to the lower spatial dimensions, there's another problem of having confinement. So instanton effects, actually, it is already known from Polakov's work. Go back to the old days in 2+1D. So there's an instanton effects which immediately confines charges. So usually it's quite hard to get a gap to U1 spin liquid in 2+1D. But it's only possible when we have many fermion components as gapless excitations to get a U1 spin liquid in 2+1D. I mean, that's why people are studying 2+1D model or experimental system with possibly fermionic gapless excitations. Yeah.
So you very briefly mentioned that what happens when you heat up this spin liquid, right? Could you just expand on that if possible? Like
Okay.
if you raise the temperature?
Well, so we can just need to consider the free energy, but not the total energy. And of course, we can do that. For instance, already erase the action for the spinouts, but we can introduce a mass bar frequency and take the mass bar sum to compute some free energy part. And then, of course, we can minimize free energy. So then suddenly we, I mean, not us, but Savary found the first order phase transition between the two phases. In the low T phase, they have a finite e to the IA average, but at the high T phase, actually this is completely zero. And yeah, I didn't have time to show the numerics results from our group, but probably in the afternoon I can show the results.
Any further questions? Okay, so if not, then we thank Professor Onoda again.
Thank you.